Hello, and welcome to Vincent Codes Finance. Today, we're diving into the world of econometrics, specifically focusing on how to estimate standard errors in panel data using Python and the linearmodels library. This is crucial for accurate empirical finance research, so let's get started. In this video, we'll cover the basics of panel data, panel regressions, and the importance of standard errors. We'll then dive into the linearmodels library, a powerful Python toolkit for panel data analysis. We'll cover how to estimate standard errors in panel data with Python and the linearmodels library. Specifically, we'll see how to estimate panel OLS regressions with OLS standard errors, white standard errors, clustered standard errors, and Driscoll-Kraay standard errors. We'll also see how to estimate Fama-MacBeth regressions with Newey-West standard errors. This video assumes familiarity with Python and pandas. If you're new to Python, check out my other videos on the basics of Python for finance. This video also assumes familiarity with linear regression. See the description for links to the code used in this video and to the blog post for a written version. First, let's understand what panel data is. In finance research, panel data is a common tool. It involves data collected over time for the same entities, like firms or stocks. Imagine tracking several firms over a decade. That's panel data. Examples of panel data include price series for many stocks, option price series at various strike prices, and firm financials over time. More formally, panel data is a combination of cross-sectional and time series data. This dual dimensionality allows us to observe changes over time and across different entities, offering rich insights for empirical analysis. Linear panel data models have the form YIT equal alpha I plus alpha t plus xit prime times beta plus epsilon it, where yit is the dependent variable for entity I at time t. Alpha I is an entity fixed effect, alpha t is a time fixed effect. Xit is a vector of independent variables, beta is a vector of coefficients, and epsilon it is the error term. The goal is then to estimate the vector of coefficients beta, our estimators, and their associated standard errors. Now, why do we care about estimating standard errors in panel data? Well, standard errors help us measure the precision of our estimators. Think of them as a gauge of how much we can trust the results of our models against different hypotheses. For example, we can test whether the coefficients are statistically different from zero using the t-test. Some tests, like the f-test, require the full covariance matrix from which the standard errors are derived. In the context of panel data, getting these standard errors right is crucial because they have to account for complex dependencies across entities and over time. To keep things simple, from now on, let's assume that the entity is a firm and the time is a year. We need some test data for this video. We'll use the test data from Mitchell-Pedersen's website. In his 2009 RFS paper on estimating standard errors in finance panel datasets, Mitchell-Pedersen compares the performance of different standard errors estimators in panel data. To accompany the paper, he published a webpage with programming advice on how to estimate standard errors in panel data with Stata and other languages, but not for Python. We'll use his test dataset to demonstrate how to estimate standard errors in panel data with Python and the linearmodels library. The dataset contains simulated data for 500 firms over 10 years. You can download the data from Pedersen's website. We'll use Panda to load the data into a data frame directly. Let's take a look at the first few rows. The linearmodels library is our main tool today. Developed by Kevin Shepard at the University of Oxford, it's a Python package that extends stats models, offering functionalities common in financial econometrics. You can install the library with your package manager of choice, including Poetry, pip, and Conda. If you use Conda, be aware that linearmodels is not available in the default Conda channel, but it is available in the Conda Forge channel, so you'll need to specify that when installing. Once installed, we're ready to dive into the world of empirical finance modeling. We'll be exploring how this library helps in accurately estimating different types of standard errors. The library is easy to use and intuitive for anyone familiar with stats models. In this video, I will use two model types, Panel OLS and Fama-MacBeth. As their name implies, the Panel OLS class is used to estimate panel data models, and the Fama-MacBeth class is used to estimate Fama-MacBeth regressions. The library also provides implementation for random effects and first differences models, and for between estimation and pooled OLS estimators. In addition to panel data models, the library also provides implementations for instrumental variables models, including two-stage least squares, three-stage least square, GMM, and SIR, and for estimating linear factor models. Like stats models, linearmodels provides a formula interface to specify the model. I will use the formula interface in this video, but you can also use the library with arrays and matrices. A key particularity of linearmodels is that it uses the indexing capabilities of pandas to identify the panel data structure. In particular, the data frame that contains your panel data must have a multi-index with the entity dimension in the first level and the time dimension in the second level. With our dataset, all we need to do is set the index to the firm identifier and the year. Before we dive into the code, let's review the matrix notation for the panel data model. This notation is useful to understand what the code is doing behind the scenes. The model can be rewritten in matrix form as y equal x beta plus epsilon, where y here is a vector of the dependent variable, the yit, x is a matrix of the independent variables, beta is the vector of coefficients, and epsilon is a vector of errors. The number of observations is n, and the number of independent variables is k. For a balanced panel in which each firm is observed for the same number of years, n is going to be equal to I, the number of entities, times t, the number of years. If the model includes fixed effects, we assume that the vector y and the matrix x are d-mean by the relevant fixed effect. It is then common to stack the observations for each entity. For example, if we have I firms and t years, the vector y of elements yit is defined as this. We can see all the observations for the first firm at the top, then all the observations for the second firm, and so on. The matrix X is defined similarly. We can see that the first row contains the observations for the first firm in the first year. We can then see that all the observations for the first firm are at the top, then all the observations for the second firm, and so on. Linearmodels will create these matrices for us from the data frame and the formula we specify. Finally, the beta vector is defined as usual. The most common estimator for the panel data model is the ordinary least squares estimator, OLS. The OLS estimator is the one that minimizes the sum of squared residuals. Residuals are the difference between the actual values of the dependent variable and the predicted values from the model. In matrix notation, the OLS estimator is defined as x prime x inverse x prime y. And its covariance matrix sigma, which is used to calculate the standard errors, is defined as sigma square epsilon times x prime x inverse, where sigma squared epsilon is usually estimated from the residuals. E is a vector of residuals. E prime E is then the dot product of the residuals with itself, which is the sum of squared residuals. We then divide by n minus k to get the average squared residual. The minus k is needed to make our estimator of the variance of epsilon unbiased. The estimate of the covariance matrix is then this big formula, which actually looks like this. Standard errors are then calculated as the square root of the diagonal elements of the covariance matrix. When looking at individual coefficients, the standard errors are all we need to calculate t-statistics and p-values. Other tests, like the f-test, require the full covariance matrix. The panel OLS class can be used to estimate OLS models with linear models. After importing it, you initialize the model using the from formula constructor and estimate the model using the fit method. Note that the intercept is usually excluded by default from panel data models because the use of fixed effects renders it redundant. We need to add it manually to the model by adding 1 to the formula. The resulting object will contain a .summary attribute with the results of the estimation. The OLS estimator is unbiased and consistent under the assumption of IID errors with zero mean and constant variance. However, in panel data, the errors are rarely IID and often exhibit heteroscedasticity and autocorrelation. Fortunately for us, linear models provide several estimators that can be used to address these issues. The most common issue in panel data is heteroscedasticity. Heteroscedasticity means that the variance of the errors is not constant. A common estimator that addresses heteroscedasticity is the white estimator. The white estimator is defined as x prime x inverse times x prime times diag of residual squared times x prime x inverse. So we have the x prime x inverse that is making a sandwich of the middle term. And what's in that middle term? Well, you've got diag of residual squared. This is a diagonal matrix with the squared of the residuals on the diagonal and 0 elsewhere. The white estimator is available in linear models as the COV type argument of the fit method. We can set it to robust to use a heteroscedasticity robust estimator. The coefficient estimates are the same as in the OLS model, but the standard errors are different and the t-statistics and p-values are adjusted accordingly. Another common issue in panel data is autocorrelation in the errors. Autocorrelation means that the errors are correlated with each other. To address this issue, we have to make assumptions about the structure of the autocorrelation. A common assumption is that the errors are correlated within each entity, so within each firm, but not across entities. This table, taken from Pedersen's paper, illustrates this assumption. Terms on the diagonal are the same as those assumed by the white estimator. In other words, the errors are heteroscedastic. The errors are also correlated within each firm, but not across firms. Under this assumption, the covariance matrix can be estimated by clustering the standard errors. This is called clustering by entity. The COF-type argument of the fit method of the panel OLS class can be set to clustered. When using this option, we need to specify the dimension along which to cluster. In this case, we want to cluster by entity, so we set cluster entity equal to true. By default, linear models does not adjust the degrees of freedom when estimating clustered standard errors with small clusters, while other statistical packages like Stata do. To get the same result as other software, we need to set group debias to true. Note that this is only needed for clustered standard errors. For the other estimators, this adjustment is done by default. We can also cluster by time. In this case, we'll set cluster time equal to true. In this case, group debias will make a difference because our time dimension is small. We can also cluster by both entity and time. The assumed structure of the autocorrelation then looks like this. We can see that in addition to being correlated within each firm, the errors of different firms in the same year are also correlated, as shown by the off-diagonal terms. In this case, we set cluster entity and cluster time to true. The panel OLS class is also called the fixed effect model in linear models documentation, and for good reason. If we go back to the original model, we can see that it includes fixed effects for the entity and for the time dimensions. Fixed effects are dummy variables that capture the constant effect of each entity and each time period. They are useful to control for unobserved heterogeneity across entities and for common shocks across time periods. In the matrix notation seen earlier, we assumed that the vector y and the matrix x are d-meaned by the relevant fixed effect. This is what linear model does when we use fixed effects in the model. In theory, we could get the same results, the same coefficient and standard errors, by adding dummy variables for each entity and each time period to the model, but this is numerically inefficient. To add fixed effects to the model, we add plus entity effects and plus time effects to the formula. The intercept is redundant in this case, so we also remove the 1 plus that we added earlier to include the intercept. Fixed effects will impact the coefficient estimates and the standard errors. So I have an error here. I typed an underscore instead of a period before summary. Let's fix that. Another common model in empirical finance is the Fama-MacBeth regression. The Fama-MacBeth regression is a two-step procedure. In the first step, we estimate the model for each time period as illustrated by the t subscript on the beta. In the second step, we average the coefficients beta t over all time periods to provide final estimates. The covariance matrix can then be computed from the variance of the coefficients across time periods. Linear models provides a Fama-MacBeth class that can be used to estimate Fama-MacBeth regressions. The usage is similar to the panel OLS class. It is common practice to use Newey-West standard errors instead of the unadjusted standard errors in Fama-MacBeth regressions to account for heteroscedasticity and autocorrelation in the residuals. The Newey-West estimator uses a Bartlett kernel to estimate the covariance matrix, which takes a bandwidth parameter as input. This bandwidth parameter controls how many lags of the residuals are used to estimate the covariance matrix. For example, if we set the bandwidth to 3, the covariance matrix weights placed on each lag is linearly decreasing from 1 to 0 over the first 3 lags and is 0 for all other lags. To use the Newey-West estimator, we set cuff type to kernel, the kernel to Bartlett, and specify the bandwidth using the bandwidth argument. In this case, we set it to 3. The coefficient estimates are the same as in the Fama-MacBeth model, but the standard errors are different and the t-statistics and p-values are adjusted accordingly. We can also use the Bartlett kernel to limit the number of lags considered when using panel OLS. This is called the Driscoll-Kraay estimator. It is an heteroscedasticity robust standard errors estimator that is robust to serial correlations in the errors. To use the Driscoll-Kraay estimator, you would use exactly the same options as for the Newey-West estimator, but with the panel OLS class instead of the Fama-MacBeth class. It seems like I made a typo here. I typed bandwidth instead of bandwidth. Let's fix that. That's it for today. If you want to learn more about the Linear Models library, check out the documentation and the source code on GitHub. Remember, mastering tools like linear models is invaluable for empirical finance research, but understanding the underlying theory is just as crucial. To that end, I also recommend reading Mitchell-Peterson's paper on estimating standard errors in finance panel datasets. It's a great resource to learn more about the different standard errors estimators and their performance in panel data. For a complete textbook treatment of panel data, I recommend Time Series and Panel Data Econometrics by Hashem Pesaran. It is a great resource for anyone interested in learning more about the estimators we discussed today. To learn about more advanced econometric techniques, I recommend Econometric Analysis of Cross-Section and Panel Data by Jeffrey Wooldridge. It skims quickly over what we discussed today, but it goes much deeper into the theory and practice of panel data analysis. I hope you enjoyed this video. If you did, please like and subscribe to the channel. If you have any questions or comments, please leave them in the comments section below. I'll do my best to answer them.